Hi everybody, this is Merlin van Veen from the Netherlands with a quick and dirty video about impulse responses. This video is intended to accompany an article which you will find in my study hall section on the website called A Track Named Impulse Response. What is the impulse response? Imagine that we have a black box. We refer to that black box as the DUT or device under test. Now suppose I were to insert an impulse into that black box and connect the output to an oscilloscope to observe the response of that black box to the impulse. That is the hypothetical question that we're dealing with. What would be the response of this black box to an impulse if we observe the outcome on an oscilloscope? Hence, impulse response. We'll look at several cases. In the first case, we'll look at what happens if I feed my impulse directly into a microphone cable and observe the outcome on an oscilloscope. Then we will look what happens for real speakers. Now I don't have the option to work with real speakers within the confinements of my office, but I can model the behavior of real loudspeakers or even subwoofers for that matter and look at similar data as if we were actually picking up the sound produced by our subwoofer with an actual measurement microphone connected to an oscilloscope to observe the output, the response to that impulse. So let's start with the microphone cable first. I'm going to do this in Reaper. Reaper is a digital audio workstation, and as you can see I have two tracks. Track 1 is the track that I will call the impulse. This is the track that contains our perfect impulse response, if there's such a thing. A perfect impulse response, as you can see, is a single sample event. It is one sample with a maximum amplitude, and you can think of that impulse response as an infinitely wideband signal with an infinitely short duration. In other words, think of every frequency running for exactly one cycle, no more no less, all the way from DC to visual light. And the amplitude of all those frequencies is identical. In track 2, we are going to observe the response to that impulse. And in track 2, I have the opportunity in my digital audio workstation to introduce some plugins, including an actual oscilloscope. So, by means of routing track 1 in my digital audio workstation to a bus, where this oscilloscope is inserted, we can literally observe the response on an oscilloscope to this impulse. Now, I would like to bring to your attention that an impulse response shows you time domain. In other words, it shows you amplitude over time. Time evidently from left to right, and magnitude from top to bottom. The value in the center is always 0, the scale is linear, and the oscilloscope, as you're well aware, will show you alternating current with positive and negative polarity. So, let's see what happens if we listen to this impulse response. Well, there you see it. Okay? You literally see the response of our oscilloscope to that impulse. Now I'm aware that the impulse, in our case, looks like a very tall pyramid, and that the oscilloscope only shows you half of the pyramid. This is for technical reasons because the oscilloscope is being triggered on the rising slope of the impulse, and that means that on the oscilloscope that rising slope is lost. Other than that, you can see that this is exactly a replica of our impulse. Think of track 1 as what goes into our device under test, and think of track 2, which I called the response, as what comes out of our device under test. And since there's no plugins inserted other than the oscilloscope itself, we're effectively dealing with a perfect microphone cable, and of course the microphone cable is expected to deliver all frequencies instantaneously without changing the time or without changing the level. And this we also know by looking in Smart. In Smart here we see the transfer function of a microphone cable. In the top plane, in the top plot, we have our impulse response on a linear scale. It's exactly the same pyramid again as we saw in our digital audio workstation. The phase response is of course flat. You do not expect a microphone cable to introduce any phase shift. There is a 0-degree offset for all frequencies. And the magnitude response is of course also flat. You do not expect the microphone cable to change the level on a frequency dependent basis. So far, so good. I can also freeze track 2 and substitute this track for a new track containing all processing. And it should not come as a surprise that if I do that for a perfect microphone cable, that the input in track 1, which is my impulse, and the output, which is the response to that impulse, that they look virtually the same. The devil is of course in the details. If I put my cursor over here exactly at the peak in track 1, we see a minor offset between the peaks, but that is due to the routing within my digital audio workstation. Other than that, the input, the impulse that goes into the system, and the output, the response to that impulse, they look exactly the same. I also want to show you that we're dealing with polarity, with alternating current. And this can be done by simply flipping the polarity in track 1. If I flip the polarity in track 1, then positive becomes negative and vice versa. I just flip the polarity, and now instead of triggering by the rising slope, I need to trigger by the declining slope, the falling slope, and that means that I have to set my threshold a little bit different, and there you go. Now you see the polarity inversion that I introduced when I toggled the phase button. Other than that, it's exactly the same story, but no longer with a positive amplitude. This time around it has a negative amplitude. It's a perfect mirror image of the impulse in the top. Let me undo this by taking out the polarity inversion and set this to be triggered by the rising slope. Massage the threshold ever so gently, and there we go. Now we're back at the original situation. So there you go. Now I want to take it up one more step. Now I am going to process my microphone cable in such a way that it will show the phase response that you would expect to see for a typical two-way loudspeaker with a fourth order crossover somewhere in the vicinity of 1 kHz. The phase shift we see over here is typical behavior that I'd expect to see in such a scenario. And if we now look in the top, then suddenly our impulse response no longer looks like that perfect pyramid that we saw in the beginning. The left-hand side still looks the same, this portion still looks the same, but the right-hand side appears to have been stretched out over time, for reasons that I will not discuss in this particular video. So let's see if this behavior is also confirmed when we observe this response to an impulse. In order to show you that, I'm going to change projects. I'm going to go to this project. And then in the top, in track 1, we again see the same impulse that we've been dealing with so far so long. The plugins that I'm using over here are processing this bus, think of it as the output, in a similar fashion as we saw over here in Smart. Okay? So all the magnitude processing that you see over here and all the phase processing you see over here, that is also going on in Reaper in my digital audio workstation. Okay, well, let's press play and observe the response of this device under test, which is no longer perfect microphone cable, but has now become a virtual two-way speaker. Let's observe the response to this impulse. And there you go. Now, notice that this response on an oscilloscope looks virtually identical to the impulse response that we see in SMART. Let me massage the time value a little bit, but the resemblance is striking. So there you have it. In track 1 of our digital audio workstation, we have the input. There's our perfect pulse going into our device under test. And in track 2, we see the response to that impulse on an actual oscilloscope showing us amplitude over time. And clearly, this is no longer a perfect replica of the pulse that went into the device under test. This signal has been stretched out over time because of the phase shift that real loudspeakers exhibit. Okay, so let's freeze track 2 and apply all the processing so that we can actually see the waveform. And there we go. Now all the processing that was in that group, was present in that group, in that bus, has now been applied to this track. And what do you know? It looks exactly the same as you see in SMART. Okay? Or in an analyzer in general for that matter. Exactly the same result. And clearly what comes out of our device under test no longer looks the same as what goes in to our device under test. Surely you would not expect to hear any sound if I scrub in track 1 in this portion of the waveform. And of course the same is true over here. In track 1, if I would scrub over here, you would not expect to hear any sound because there's no amplitude. Evidently, if I scrub around the peak in track 1, you would expect to hear sound because there's data, there's amplitude. If we look at our response to that impulse, which is down here, again, you would not expect to hear sound if we scrub over here because there's no data. But unlike the original impulse that went into the device under test, now in the output there is amplitude. And if I scrub here, you would expect to hear sound. And it doesn't require a lot of imagination to understand that the portion that we have over here is later in time than the portion we have over here where the peak occurs. So clearly, not everything is being delivered simultaneously, unlike a microphone cable. Okay, now I want to show you even a more dramatic example of a subwoofer. I'd expect the phase response of a regular vented enclosure for a subwoofer with an operational bandwidth from 31 Hz to 125 Hz. I would expect that to look like we have over here in SMART. There you go. Now we clearly see a lot of phase shift, which is perfectly normal when it comes to subwoofers. But I don't see any impulse response, at least not on a linear scale. And this scale is exactly the same as the one that we have on our oscilloscope. It will show you alternating current with positive polarity and negative polarity with values from 0 all the way to positive 100 and 0 all the way to negative 100. Because whenever you're dealing with band-limited signals, you lose amplitude for reasons that I will not disclose in this particular video. But in the article called A Track Named Impulse Response, you will find more information explaining why there is no amplitude. So I need to zoom in all the way to less than 1% to see the impulse response. Now clearly this no longer looks like the pyramid that we started out with, the perfect pulse. This guy has been stretched out over time by several dozens of milliseconds, because I would like to remind you that one division is 10 milliseconds. So there's a lot of time stretching going on, if you will. And clearly the response of this device under test, which is a virtual subwoofer, to the perfect impulse is no longer a perfect replica. So let's see if we can also observe this on a real oscilloscope in our digital audio workstation. There we go. Again, in track 1 we have the input, our impulse response. There it is. There's our perfect pulse. And track 2, which is the bus where I've routed this impulse response to, has been processed in exactly the same way as we see over here in SMART. and it has the oscilloscope. So let's look at the outcome, the response of this particular device under test to that impulse. There we go. And what do you know? This picture is now the response to the impulse. And clearly again, if we keep those guys next to each other, then the resemblance is striking. So there you see it. Impulse response is the response to a perfect impulse of a particular device under test. So, like before, I will freeze this track and then we will see the same waveform with all processing applied. Okay. Now, again, because we're dealing with a band-limited signal, at first glance I have no amplitude, but that can very easily be remedied by normalizing this track, which is effectively increasing the amplitude. And there we go. Wow. So I need to zoom out, 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 zoom out. And now we see the response to that impulse. So here you have our input, which is the perfect pulse going into our device under test. And this is what comes out of our device under test. And clearly that is no longer looking exactly the same. Also in our digital audio workstation, you can see that this signal has been stretched out over several dozens of milliseconds. Okay, this is in seconds, but that would be roughly about 100 milliseconds, give or take. So again, time stretching. And like I said before, with our two-way loudspeaker, in track 1, which is our input, if I scrub over here, you would not expect to hear any sound. Same when I go over to this portion in this track, you would not expect to hear any sound. Only if I scrub around the peak, you would expect to hear sound. However, if we look at the response to that impulse of our device under test in track 2, if I scrub over here, you would not expect to hear any sound because there's no data, there's no amplitude. However, unlike our input, in the output, when I scrub in this portion, there is very much signal, there is very much data, there is amplitude. And clearly, not all frequencies are being delivered simultaneously because everything we see over here is of course later than the initial impulse response that we started out with. Okay? You can see there's a lot of stretching going on because subwoofers typically exhibit even more phase shift in comparison to regular two-way loudspeakers. So, the waveform that you and I are used to seeing in our digital audio workstation, whether it's Reaper or Logic or Pro Tools, is literally an oscilloscope. It's the same scale as we saw on our plug-in oscilloscope, and it's the same scale as we see on the linear scale in the impulse response in Smart. And therefore it will show you evidently alternating current with positive and negative polarity. So there you have it. 3 times the same story. Once in Smart, which shows you both the time domain, which is amplitude over time, and the frequency domain, which is amplitude over frequency and time over frequency. And you saw it on an actual oscilloscope in our digital audio workstation. And you see that when we freeze the tracks and all processing is being applied to that track, then we see exactly the same result. We see the actual waveform with the applied processing, and clearly input and output no longer look the same. So if we condense that in 3 final slides, then this would be the microphone cable example. Here you see our digital audio workstation. This is the impulse that goes into the device under the test, and this is the response to that impulse. And clearly for a microphone cable you would expect those two to look identical, because after all a microphone cable does not introduce any frequency-dependent phase shift, and it does not change the magnitude response over frequency. It is a perfect conduit, if you will. It is electricity running through copper close to the speed of light without changing pretty much anything. And also, if we look at the oscilloscope, we see exactly the same outcome with a minor detail that for technical reasons that the rising slope has been chopped off. But other than that, this shape is exactly the same as the other ones that we have over here. Then we changed our microphone cable with virtual processing into something that looks like an actual two-way loudspeaker. This is what I would expect to see when I deal with a regular two-way loudspeaker with a fourth order crossover, somewhere in the vicinity of 1 kilohertz, which is over here. And clearly that impulse response no longer looks the way it did before. Okay, here we see it also in our digital audio workstation. This is the impulse and this is the response to that impulse. And clearly those two no longer look the same. Also the oscilloscope confirms this. Because of the phase shift inherent to real loudspeakers, the response to the impulse has been stretched out over time, and clearly not all frequencies are being delivered simultaneously. And finally, our subwoofer. This is what I would expect to see when I deal with a regular subwoofer, lots of phase shift, and a signal that has been severely stretched out over time. If we look at this processing, if you will, in our digital audio workstation, then again, in track 1, you literally see the impulse going into the device under test. And in track 2, which is the response to that impulse, we see that these no longer look identical. The response to this impulse has been stretched out over time, just the way we saw it happen in our analyzer, and also the way we see it happen in our oscilloscope. So there you have it. Impulse response is the response to an impulse that we feed into our device under test and observe on an oscilloscope. Okay, for more information regarding impulse responses, I encourage you to read this particular article, and I hope to see you next time. Thank you for your time and patience. Bye-bye.